Welcome to the WP5 Demonstration 1.1 of the Verge-Project. This demonstration is developed by King's College London in collaboration with our European partners under the Horizon Europe program. This demonstration includes 3 integrated scenarios enabling edge intelligence for XR. First, we use wireless split learning between XR devices and MEC servers over a 5G testbed, reducing training latency and transmission while maintaining accuracy. Second, we implement a federated split learning framework that supports scalable, privacy-preserving model updates across multiple devices. Third, we showcase dynamic XR rendering task offloading using HoloLens 2 and reinforcement learning, optimizing rendering location in real time to reduce latency and device workload.
Hello everyone, we are a research team from King's College London. Today, we are pleased to present our project titled Wireless Split Federated Learning between the Edge Server and XR Devices. This work focuses on collaborative learning between edge servers and extended reality (XR) devices, aiming to improve the efficiency and privacy of federated learning in wireless network environments. We introduce the background and motivation for our work. With the emergence of 6G AI-native networks, there's growing interest in split learning (SL) under wireless environments. However, this introduces a fundamental trade-off between computation and communication, especially when training deep models across XR devices and edge servers. Our motivation stems from several challenges. First, there is no standardized testbed to evaluate such systems. We aim to provide a system-level evaluation using Smart Edge Open together with SDR and the OAI platform. This allows us to study the impact of the split layer, as well as critical system metrics such as accuracy, latency, and overhead. Ultimately, our goal is to advance Edge AI technologies for future 6G networks. On the left, we have a GPU server running the edge-side split learning model. It handles the heavy computation tasks and coordinates with the user device over a wireless link. At the center and right, you can see 2 USRP devices, one acting as the server-side radio and the other as the user-side radio, user. These are used to establish a real-time wireless connection using the open-air interface stack. The small black box on the right is the CPU-based user equipment, CPU-UE, which runs the client-side model and transmits intermediate data to the server. The neural network architecture we used for split learning and the cutting strategies we evaluated. The model follows a PointNet++-like structure, processing 3D point cloud inputs on the user device. We designed several cutting points, from Layer 1, FP1, to Layer 4, FP4, where the model can be split between the user and the edge server. Each cutting point results in a different output tensor size and computational load. As shown in the table, earlier cuts like FP1 reduce the user's computation but increase communication load, while later cuts like FP4 shift more computation to the user but reduce the size of the transmitted data. This slide illustrates our end-to-end system setup and its runtime environment. We implemented a 5G communication link using USRP devices and the open-air interface (OAI) protocol stack. The split learning setup is also deployed here, with the first layers running on the user side using a CPU-based device, and the remaining layers on the GPU server. The terminal windows shown in the images demonstrate the real-time execution of training processes on both the user and server sides, verifying that the data is transmitted, processed, and returned correctly across the wireless channel. This slide shows the runtime setup and experimental results of our semantic inference task. On the top, we present the real-time execution environment where the CPU user device runs the front part of the neural network and communicates with the edge server. At the bottom left, we illustrate the semantic information inference accuracy across different cutting layers. As we can see, all configurations gradually converge with training, but deeper cuts like FP3 and FP4 achieve slightly higher accuracy. This confirms that although earlier cuts reduce computation on the user side, they may compromise performance, highlighting the need to balance between device efficiency and model accuracy in practical deployments. This slide presents the experimental results of our split federated learning framework under wireless communication. On the left, we show the communication data for different split layers. As expected, earlier splits like Layer 1 result in larger uplink packet sizes, since more data needs to be transmitted from the user to the server. However, packet loss remains low across all layers, indicating a stable link. On the right, we evaluate the overall time delay per batch, broken down into 3 components. Client computation, in blue. Edge computation, in red, and communication overhead, in green. We observe that splitting at later layers significantly increases the client-side workload, while earlier splits reduce device burden but increase communication costs. This again highlights the trade-off between communication efficiency and device computation, critical in XR applications where user devices have limited resources. Then, we have this demo titled, FSL, a federated split learning framework over 5G wireless communication networks. It demonstrates how federated split learning can be applied in a 5G environment. This slide illustrates the overall architecture of our federated split learning framework over 5G. It consists of two main components. On the right, the split learning process allows each user to compute the first few layers of the model locally and send intermediate activations to the split server via a 5G network. The server completes the forward and backward pass and returns gradients. On the left, the federated learning process aggregates the local model's first layers at a centralized server and distributes the updated model back to all users. All communications are performed over open-air interface-based 5G wireless links, ensuring real-time and low-latency training. The entire federated split learning framework consists of three main components. First, the aggregation server. It is responsible for collecting the local model updates from different users and performing model aggregation, which is a key step in federated learning. Second, the split server. This server handles the intermediate activations and gradients exchanged with user devices. It completes the forward and backward passes of the server-side model in the split learning process. And third, the multi-UE program running on the right side. This part simulates multiple user equipments, each performing local computations on their partial models, and then communicating with the split server over the 5G network. First, we initialize the 5G communication system using open-air interface on PC number 1. Step 1. Start the core network, also known as EuCNC'25. This will launch all essential 5G core components, including AMF, SMF, and UPF. Step 2. Wait for all components to fully start. You should see a message indicating that the services are up and running. Step 3. Launch the GNB, or the 5G base station. The GNB connects to the core and communicates with user devices over the 5G radio interface. Step 4. Optionally, launch FlexRIC, an ORAN-compliant RAN controller, for enhanced control and slicing features. Next, we move on to the user equipment, or UE setup. We use two UE PCs, and on each UE PC, we start the UE process. This connects the devices to the 5G base station we launched earlier. Once both UEs are running, we can check their IP addresses using the ifconfig command on each machine. With valid IP addresses assigned by the 5G core network, we can ping each other to test if communication is successfully established between the two UEs through the 5G network. This confirms that the entire 5G data path, from GNB to core network to UEs, is working correctly. Next, we run the three previously mentioned components on separate virtual machines. The aggregation server, the split server, and the multi-UE program are each launched in their own VM environments, to simulate a realistic distributed deployment scenario. This experimental results show that our FSL approach achieves a good balance between accuracy and transmission cost in 5G scenarios. FSL maintains high skeleton extraction accuracy, close to SL, while significantly reducing packet size compared to FL, making it efficient for edge communication.
Welcome to the Verge-WP5 Demonstration 1.1, focusing on dynamic XR rendering task offloading. This demo is developed by King's College London in collaboration with European partners. It shows how edge intelligence enables real-time XR rendering through AI-based decision-making. XR teleoperation requires high data rates and ultra-low latency. However, devices like HoloLens 2 have limited processing power for complex 3D scenes. To address this, we offload rendering to edge servers via 5G, using the HoloLightstream SDK. Our goal is to reduce XR device workload and enhance rendering quality. A reinforcement learning model dynamically decides whether to render locally or offload, based on network and system conditions. This is our system setup. Two GPU servers with NVIDIA A5000 cards are used for edge rendering and local rendering comparison. The XR app is built with Unity 3D and deployed on HoloLens 2. It connects to a Docker container on the edge. The container hosts the RL model, which monitors latency and bitrate to control a flag called render on PC. This flag determines the rendering location. Switching is done in real time to ensure seamless transitions. All components are integrated with a 5G testbed using USRPB 210 radios. Here we show the live setup. The user wears the HoloLens headset while a laptop displays the projected screen. This helps validate the real-time performance of offloading. This diagram shows how the system works. The HoloLens connects to the Docker container. A variable called render on PC decides whether to render on the server or locally. The headset polls the value regularly. When network conditions change, the container updates the flag based on latency and bitrate. This allows dynamic switching between rendering modes, optimizing performance. On the implementation side, we use a FastAPI server inside Docker to expose GET and POST endpoints. The HoloLens sends system data, and the server updates the render on PC flag. Terminal logs confirm constant request exchanges. Visual outputs include 2D video and semantic feature maps, supporting real-time control and explainability. The user starts by launching the HoloLight Stream app on the HoloLens 2. It connects to the Edge server using a fixed IP address. Based on render on PC, the system selects between local or edge rendering. These frames show the same XR interface rendered in both modes. This proves the offloading logic works in real deployment. Here is an example of local rendering. The scene is generated on the HoloLens GPU without relying on the network. This ensures minimal delay, but quality may be limited by the headset's resources. Local rendering is ideal when connectivity is poor. Now we show edge rendering. The server processes the scene using an A5000 GPU and streams it to the headset in real time. Thanks to higher computing power and 5G speed, the image quality improves significantly. This offloads processing from the device and ensures better user experience under good network conditions. This demonstration is part of the Verge-Project, funded by the EU's Horizon Europe program under Grant Agreement 101,096,034. The views expressed are those of the authors. UK partners are supported by UKRI through grants awarded to Samsung UK and King's College London.